I hope that's the only one. Anyway, okay, so let's go back here. Good afternoon, everybody. It's a real pleasure to be here. I understand that we have a diverse audience with experts in quantum computing, but also end users that are more interested in understanding how the technology may benefit them. So what I'll do today is I'll try to address both groups. So I'm going to give you an overview of the technology that underlies the products that we develop at Q-Control to make quantum computers useful, while at the same time highlighting how we are making them accessible to the end users. And then towards the end of the presentation, I'm going to be talking about how the error suppression techniques that we adopt are really crucial to the framework that's going to take us from the NISC devices that we have today all the way to the large-scale fault-tolerant quantum computers in the future, right? All right, so the starting point of our discussion is something that I imagine many of you are familiar with or have already heard about. It is the fact that quantum computing is extremely susceptible to hardware error, be it for fundamental quantum reasons or for the imperfect way that we build those devices. The fact is that hardware error is what leads to failure in algorithm executions, and therefore is the major bottleneck that we have to deal in our industry today. All right, so it's exactly this problem that we at Q-Control are uniquely focusing on solving. And we do that by developing infrastructure software that connects the bottom layers of the quantum computing stack, mainly the hardware itself and the control electronics on those systems, all the way up to the more abstract layers like the algorithms and the programming framework. And what lies in this middle layer is all the necessary error suppression technology that actually enables the execution on those devices to be functional. So let's take a closer look inside this technology. So under the hood, what we have is a fully automated pipeline that suppresses errors wherever they occur in your quantum computation. So if you look at those purple boxes there, they represent the different stages where we actually address the problems when you are trying to execute something in a quantum computer. So on the left-hand side, you have an input that's going to be the user sending or submitting a circuit to run on a quantum computer, and we go through multiple steps there. Now, most of you are familiar with, when you talk about the quality of a quantum computer, a number or a figure of merit that comes quite often is gate fidelity, right? So we talk about how many nines do you have, what is your gate fidelity. But this is, if you only think about that, you're actually missing a whole lot of sources of errors that happen during your calculation. So what we do here is that we suppress errors in multiple stages. We do suppress errors at the gate level. So we try to design faster and better gates. So this is, let's say, that's this step here. Then we also look at introducing extra operations to suppress other sources of errors. For the technical people in the audience is, for example, the introduction of pulses of dynamical decoupling techniques. Now, we also do this, all those operations and those solutions at the lower level, but we also look at the circuit level. We look at efficient ways of compiling your circuit. How can we do the compilation to reduce as much as we can, for example, the number of 2-qubit gates on the device, because that's the major blocker that we have. But we also have to think about how do we map the logical qubits that the user sends into the physical qubits on the devices, because those qubits, they are not the same. The device is not homogeneous. So you have to think about how, for example, imagine that you have a machine with 156 qubits and you want to run a circuit with 10. What are the best 10 qubits that you should be using that machine? So this is a very hard problem to solve, but it's part of this whole pipeline that we do. Now, as a software company, we want to package all these progress that we've made in terms of research into a product. And we do this with this product that's called FireOpal, that really abstracts away all this information. If you really want to get good results from your quantum computer, you just have one line of code that you can execute and get all this pipeline available for you. Now, talking about ease of use, we are very excited with the recent announcement from IBM that they're going to be launching the Qiskit functions. So this is third-party functions that are going to be available on IBM systems, and we are very proud to have 2 of our functions available in the platform. That means that if you have access to the premium IBM machines, you'll be able to get access to those functions. One of them is this performance management, which is exactly what I've just showed you in the previous slide. So this whole pipeline of error suppression is going to be available through the performance management function. That's going to be very easy to adopt and use. And the other one is the optimization solver that I'm going to come back to that in a couple of slides. All right, so I guess that I mentioned a little bit about the techniques underlying the solution. I talked about the ease of access, but I guess that the major question and the most important thing is what value does it bring to the user, right? So, and what we have here using this pipeline is orders of magnitude improvement when you are trying to execute circuits. For example, you have a 10 time factor, for example, in terms of the depth of the circuits. So you can run circuits that are 10 times deeper, meaning that you have more operations that you can execute. You can execute algorithms that are more complex than if you are not using this technology. Also, the other important thing is that because we reduce the baseline error on the device, that means that you don't really need to run as many shots, for example, to get good statistics. And if you're running things on the device, you know that number of shots represents two important things for you: time on the machine, and time represents costs because you're paying to use those machines, right? So you have a reduction, a very significant reduction in costs just by lowering the error and the necessity to run shots for statistics. But the most important part is really kind of what you get in terms of quality when you're running your algorithm. And you see 3 orders of magnitude in multiple benchmarking algorithms when you are looking at the success probability when you're running this on actual devices. Now, all of this has been validated and published in peer-reviewed journals. So I hope that you can read that on the slides, but if not, I mean, we have a page with all the technical manuscripts in our website. This thing was not only validated by us in our own experiments, but users have been adopting these solutions and actually running their own experiments. And this is, we are very proud to show, for example, the world record 33-qubit quantum phase estimation using this pipeline that was able to run with 5 times more qubits than the previous record result. And this is the result on this paper on the archive there. And we have quite a few other examples of users reporting these kinds of results. All right, so let me jump now into, let's say, the more applied side, because I mean, of course, I mean, this whole pipeline is improving the algorithm execution and so on. The whole benchmark that we've done were on, let's say, typical algorithms that people use, like Bus-Radar, quantum phase estimation, quantum Fourier transform, and so on. But now, for the next device that we have nowadays, let's say the most promising applications are coming from classical problems of combinatorial optimization. And this is where we've been engaging with multiple partners and customers, and I have a few examples here. We first started with Transport for New South Wales back in Australia, looking at routing problems for them. And then we worked with the Australian Army, also looking at very interesting problems, really hard problems where you have lots of constraints that you have to consider, and they become very quickly hard to solve classically. And more recently, we've been engaging with the Department for Transport in the UK and Network Rail, looking at scheduling problems. They want to see, for example, the incoming trains in the station, in London Bridge Station, for example, knowing how to allocate the platforms, how much time the train stays there, and so on. So all those problems, they are based on, I mean, the most common approach in the community right now is to use the hybrid algorithms. So in those hybrid algorithms, what you do is that you combine, let's say, execution, some hard execution of quantum circuits together with a step that is a classical optimization. So you run your quantum circuits for the technical people in the audience. So your parameterized quantum circuits, you try to then classically optimize for those parameters to find the solution, right? Now, if you think about what I was describing before, right? So when we do all that error suppression, all that pipeline, we do that for a generic circuit that the user is going to send. I don't know what you're going to send to the device, therefore I have to have that pipeline optimized for some sort of average performance, right? But we know that we have some information about the specific algorithm that the user wants to run. we can actually do some specific and tailored compilation for that system as well. And that's what we've been doing with this QAOA. So actually you have a specific pipeline for this sort of problem because so many users wanted to implement that. So I have a specific compilation focused on QAOA. We also have specific post-efficient gates in the system's parameter reduction. And then also we optimize the classical part as well. Right? So this is also a well-known issue that, I mean, what is the best classical optimizer that you should be using in those problems, right? So it depends on the landscape and things like that. And then we have also post-processing in the output solution. Now, again, with the same spirit that we want to make those things accessible to the end user, we put this into a single function in that product in FireOpal, that you just have FireOpal solve QAOA. You can input a graph that you want to solve, then you design your cost function, and with that you can just kind of execute and again, abstract away the technicalities inside. Now, this is really kind of, I mean, it is an exciting result that we published a few months back, or even less than that. But we did optimization using 127 qubits on an IBM device. And it was also the first time that we saw an optimization problem being solved more efficiently in a gate-based model than in an annealer system. So what kind of problem did we use to demonstrate? So one example is this max cut problem where you have this graph. And so the problems that I was mentioning before about routing and so on, some of them can be put in this way. So you have a graph, lots of nodes, some connecting edges, and you want to split this graph into two subgraphs and maximizing the edges crossed. Now, it's easy to do this for a small graph, but if you have a larger graph, becomes quite quickly hard to solve classically, right? And so the hope is that using those quantum systems, you can try to see what you would get. So actually what we showed is that we can actually solve those kinds of problems at utility scale. We solved for 156 qubits, that pretty much the whole device on IBM, with this graph with 3 regular cuts. What we see here in red is the distribution that you have with brute force, where we just look at the outputs and you just do a histogram with the outputs and you see what are the cuts that you get, right? What you see here is that actually you don't get, in any instances that you're running in this brute force, you don't really get the actual value of your max cut in your solution. And running it brute force is pretty much what we get when we're running directly on the hardware. Now, when we implement that optimization function, that's what we get on the right. So not only the whole distribution shifts to the right solution, but we actually have lots of quite a significant number of your output here finding the right solution of your max cut problem. So it is really kind of a record in terms of the number of qubits that you can use, and this is really kind of pushing to the region where those are the problems where classical is becoming harder to try to solve. Then we also looked at a slightly different problem with high order optimization here that we are using. We started with it is a spin glass Hamiltonian for those on the technical side in the audience. That was I think was a group from Los Alamos that published that, and they used an annealer to get the minimization. So you want to try to find the ground state energy calculation. So in this case, instead of trying to maximize something, you're trying to minimize, so the good results are actually on the other side of your graph. And then you see that the results that we got directly using IBM, we actually have this, again, the distribution really pushing to the minimum there in a big amount, in that case 20% of the counts in your experiments, really giving you the ground state. Right? So we're really approaching this region where we're getting towards utility in those systems. All right, so that's where we are right now with those NISQ devices. We are using the whole device, which is really interesting. That means that if you want to go further, we're going to need bigger devices, right? So when we have access to that, that's why we're going to keep pushing from 156 to 100, 400, whatever we get access to, right? Now, when you think forward and you look at and you think about what the industry is talking about, and kind of we look at the roadmaps from hardware providers as well, and you heard from André's talk previously. So lots of people are thinking about also error correction. This is important, right? So what we do is error suppression. We are trying to suppress the baseline errors on those devices, but eventually errors occur. And then you also want to correct whenever those errors happen, right? So it's a combination of two things. And actually, to extract the maximum value of this, you actually have to combine the different strategies, right? So you can't really kind of think, okay, we have this device today, and then I'm going to have fault tolerance tomorrow, and there's going to be more like a continual evolution from one to the next. Now, one important thing to talk about when you're thinking about error correction is really the overhead that we need. So you probably have already heard about that, but when you're trying to encode your error correction, you think about the logical qubits that you can have, you need lots of physical qubits to do that encoding. Not only that, but you need a lot of operations to correct for the errors that occur. So there's a lot of overhead, right, from 90, if you're really, really optimistic, or 99.9% of qubits. If you have a device, 99% of your qubits are actually used for error correction only, not for the actual calculations, right? And this is an issue. Now, it's the way that we like to think about this, I mean, how this connects to the first part of my talk in terms of error suppression, is this analogy here. So if you think about the error correction as being the air conditioning that's trying to cool down a room, right? But you have the doors and the windows open, right? So you have a large amount of errors. What this does is that you have to really pump hard your air conditioning. So you're really trying to get a lot of resources from your system to actually cool down. Not only that, but you're probably not going to be able to cool down to the temperature that you wanted to, right? Now, when you combine this with error suppression, what we do, I mean, error suppression is the equivalent of closing the windows and the doors, right? So we lower the baseline error of the device, therefore making it easier to implement the error correction because you have less errors to correct. That's the idea. So that's how you see those techniques working together in the future. And this is not only just a nice idea. I mean, we have some of our customers from Nord Quantique in Canada, where they work with bosonic qubits and superconducting devices, and they implemented the error correction, and they showed that when they combine the error correction with our error suppression techniques, they can actually surpass the break-even point. Break-even point is basically because, as I told you, because you have to introduce more operations to correct, because those operations are not perfect, you may actually be introducing more errors than you are correcting, right? So the break-even point is that it is worth doing error correction rather than doing nothing. And they were able to surpass that break-even point, which is an interesting thing. Now, we are really excited with combining those technologies, and coming soon to our pipeline, we are also going to introduce an efficient quantum error correction stage, right? And we've been doing experiments on that, and we actually have shown that using the techniques, so I mean, with what we can do right now, in this case, we are trying to generate a very large entangled states. That's with those green qubits in this IBM machine, and the yellow one there as well. And the red ones are some measurement qubits where we measure parity. I'm not going to go into the details, but the important thing is that we see that we're combining all those techniques, we can actually generate a GHZ state, or a high entangled state with, in this case, 60 qubits. Actually, we have more recent results of 75 qubits, which is, from what I see, it's a kind of the largest one that it is in the literature. Right, so just in kind of the last couple of minutes that I have, the way that I see is really kind of this continuous kind of trend where we are in this niche area, but we are also in the area that many experiments are showing, going through that break-even point, right? Even after you go through the break-even point, then you may still not be kind of an advantage to use quantum error correction because you have so much overhead that, for example, I showed that we can solve QAOA with 156 qubits. So how many physical qubits do you need to have in an error correction system to have back 156 logical qubits? So that's kind of the journey that you have to do, is to go work together, hardware providers, software engineers, all the way to kind of go to the fault-tolerant quantum computation. And with that, I'd like to thank you, and my final message disappeared again, so I guess that this background slide disappeared. But the message that if you want to talk to us about those problems and those solutions, we have a booth up here, so you can come and talk to the team. And also, if you're here in Berlin, you are always welcome to visit our office. That's really central here in Berlin. Well, thank you.